So good morning and good afternoon. Good morning and good afternoon and welcome to this webinar. So this webinar is born from the necessity to analyze the significant change in freshwater levels within Italian karst aquifer over the past decades. So, analyze the historical data is notably that the piezometric level of the Murge Basin aquifer has dropped by 10 meters over the last 6 years, resulting as a deficit situation signs in the middle season of 2022. Today, monitoring this consulting making for Puglio region is the sense and the meaning of starting today monitoring and efficiency enhancing with the enhancing technique combined with the subsurface planning and can ensure the optimized regulation of water or freshwater resource through analyze the integration of consumption data with aquifer recharge data. So we are trying to explain the geological context of the Murge Basin aquifer. In the first slide, you can see a real cross section that is a complex aquifer with multi-level aquifer, fractured karstic, and also we have three parts. We have the first part that is the Alta Murgia Ban Plateau. You drop the level of piezometric aquifer around 200 meters 18. So the second part is the central part of aquifer that is delimited by the normal faults, normal Cretaceous faults, and so this part is the low part because it is filled by flysch sediments and Puglio quaternary sediments. You have the calcarenite gravina and you have the Puglio sediments in this part. So we have different types of circulation and wave of recharge of the aquifer. And in the second part, that is like a boundary of 50 kilometers from the sea. You have a boundary from 50 kilometers, around 50 or 30 kilometers from the sea. You have the superficial aquifer and aqueducts with problems, with trouble also of marine saline intrusion. So we are discussed. We have the first presentation of the first results. We underlined that we can make a general comparison. We cannot make a general comparison to other karstic Italian aquifer because it is a very structural and geological structural situation. This monitoring was made for the middle part, so the faulted part between the superficial aquifer and aqueducts, and was made for this part. You can see the total cross section is around 40 kilometers. So for the aqueduct, then this part is around 50 kilometers from the sea. The topics is how monography can support water source assessment, why use monography to monitoring karstic aquifer in Puglio, join monography data with well logs data and series data in karstic aquifer per region, water resource assessment and management and support regional water resource, time series analysis of water needs requirement. Take notes for actual situation about the water requirements, availability and efficiency, support regional activity in new well exploration and underground storage system. You can see that the topography about how monography works. So this is the monography is a new technique for that is based on a physical approach. Muon topography is emerging geophysical imaging technique that is used naturally occurring cosmic ray muons to create image of a large geological structure, similar to medical X-ray, but not on a geological scale. Muography can relieve density variation underground, making valuable tools for water resource exploration and management. Unlike conventional methods that requires activity energy source, muography passive measure cosmic particle continuous arriving from the atmosphere. So it's a natural technique at passive because that use muons, that is natural cosmic particle array, and the single muons relief can install it in the subsurface. So it's very easy if you have a karstic system that in this case the karstic system allow the installation of muography for facilitate the installation of muography for interpolate the data. Which is the principle. Muography can identify saturated zone, aquifer thickness, water table variation, aquifer boundary, useful for water utilities, agricultural, mining, desert groundwater exploration. An example is a sandstone aquifer, dry rock, water saturated, is typical effects for water saturated between 2.1 and 2.2 density, effective bulk density. Muon attenuation detects this difference of density between weighted rocks and saturated rocks. High cosmic, so the principle is simple. High energy cosmic rays collide with Earth atmosphere, producing muons that travel toward the surface. When muons pass through geological formation, dense rock absorbs more muons. Low density material allows more muons to pass. Water-filled zones have density intermediate between air-filled activities and soiled rocks. The attenuation is following the following equation. E is detected muon intensity, E0 is incoming intensity, P is material density, X is path length, U is attenuation coefficient. So by measuring muon flux for multiple angles, scientists reconstruct 2D and 3D map. Muography is becoming a completely tools for hydrogeological mapping and monitoring rather than other surface technique like geoelectrics or magnetometrics or like this. It is a unique capabilities to image large subsurface mapping density structure with non-invasive method, and over long periods is particularly promising for strategic groundwater exploration, dam and live safety, karst and volcanic aquifer, mountain water storage, climate resilient water resource and management. Laser detector technology can be assisted also by tools made with artificial intelligence and integrated with other geophysical technique to create an 3D and 4D models, especially if you are working with serious data with a long time like 4 or 6 years. So the advantage is that this technique is passive. You have no artificial energy source, so you don't have to filtering the artificial energy that you improve, for example, in seismic acquisition or other else. Deep penetration can image hundreds of meters to several kilometers depending on geology, on the subsurface geologist. Continuous monitoring, environmental friendly, no drilling or explosive required, high safety, minimal impact. So limitation, we have a clear disease some limitation for disease travel for long times acquisition, so you need to set planning the reinstallation of detectors, complex model inversion, resolution decrease with depth, small targets hardest, advanced computing needs. So calibration required, the atmosphere correction, typical water resource, groundwater exploration, you have aquifer research, karst hydrology, so we have several applications from groundwater exploration. Also, we have several applications for glacier hydrology, for volcanics. In all kind of volcanics, we can apply tomography also for detect the change in mass balance or also in presence of aquifer, mining hydrogeology, and in this case we are working for karst hydrogeology with cave and conduct mapping, and so we have several benefits to with these ambients for this typical hydrogeological context. This image was extracted by an acquisition in central part of Murge. You have the first result, imaging 2D, 3D of subsurface with like tomography. You have the distribution of water in a cross-section distribution of water in subsurface. We can change also the spatial grid and spatial grid and resolution, and integrate all of the data with tomographic electric and other types of monitoring, hydrogeological monitoring. So finally, you have this image. This is a cross section with the density image. Red colors and yellow colors represent the measured concentration of water. Why use tomography to monitoring karst aquifer? So we just explained, because to monitoring the karst aquifer you need to have a spatial resolution, a medium spatial resolution, so a useful timeline to get a clear picture of the state of aquifer. Between 0 to 3 months, you planning setup and make a site selection. We are making site selection, simulation and instruments installation, data collection, continuous monitoring, and collect significant data. Data analysis, the 3D imaging and temporal analysis of water content between this period, and a clear picture reliable of map, resource and trend evaluation for informed management. You have the following type of this tomography. In this case you have a deep penetration, highly sensitive to water, cost effective and phase, ideal for protection. The main use: monitoring water storage, early warning, map aquifer structure, support decision, and the main use is this for also to make like a photograph, and also a provision of data and support administration decision. Tomography is providing a non-invasive technique for monitoring karst aquifer in Puglio, where groundwater storage is highly. We have a highly heterogeneous situation and difficult to image with a traditional method. Cosmic Moon, natural penetrating rocks, allowing a 3D density map for underground voids, circuit of oil field. Key advantages include continuous monitoring, no drilling impact. So the spatial resolution, it depends on number of detectors, while temporal resolution range can change. This enables medium to have a clear situation, like we do in this work. The monitoring is the minimum period to 6 months to 24 months, tracking on rechange interpretation and seasonal variable, improving water resource estimation and support also the sustainability of aquifer. Comparison of technique for monitoring casting aquifer. Why use muography? There is non-invasive 3D time-lapse, so you can select a window time-lapse to monitoring, sensitive to water content. If you are making a comparison with muography with other techniques like electrical resistivity, seismic method, ground penetration radar or boreals data, you can see you have also some excellence and sustainability difference, because principle, we have just explained the principle. So with detection natural cosmic array, so you don't need nothing to make, because we are all of days immersed in this cosmic array. What is the image? Density variation, avoid fracture and water field zone. Advantages: you have non-invasive 3D imaging of a large volume, sensitive to density, water content change, time-lapse monitoring, and this. So instead, if you are comparison with other technique, you have that is, for example, tomography. We can have a small extension. You need to apply this much more times. Also seismic, but have deeper penetration than RT and GPR. So boreal data is essential to calibrate, to have a calibration or a comparison with the geophysical data. The discard, not advantages. We have a low spatial resolution. The spatial resolution is between 8 meters to 50 meters typical, require long-term acquisition. We just say, so the minimum term of monitoring acquisition is 6 months. Initial cost of detection, so we have an high initial cost of detection, but the advantage is that you can easily install detectors in karstic ambient. Instead of this, electrical resistivity and ambiguity to interpretation, affected by the presence of the surface quaternary deposit. Also, seismic method require expensive logistic and complex interpretation. Georadar is usually have a shallow penetration minus than 20 to 30 meters. You have so this is non-invasive technique, and another advantage that is cover a large volume, a large 3D volume, instead medium of RT and small of GPR, and very limited points about boreal data that is all necessary to calibrate to have a comparison test. Depth range is so the depth range is between 50 to 50 meters, and you have a relative cost high to initial, low operating. The suitability for karstic aquifer in Puglio. We have an excellent for imaging hiding the voids and monitoring water content change. Muography provides unique and non-invasive 3D time-lapse imaging and density water content in karstic aquifer. Techniques and particularly valuable for long-term monitoring in Puglia. Instead of this, for example, GPR ground georadar are useful for near surface mapping, and but boreal data are essential for calibration, but not sufficient for mapping a large part. How you can join muography data with well logs data is essential to make a comparison of acquired muography data with well logs data and series data for karstic aquifer. Integrating the data with demography, with well logs and long-term hydrogeological series data provide a powerful framework for predicting the behavior of karst aquifer. So one of the topics of this work is tied to establish the behavior of this karstic aquifer. So is establish a provisional model of the point of research, studying the point of research, underline the point of research, study, underline the quantity extraction, and understand which will be the behavior of the aquifer. So to do this, you need also the calibration of data with well logs data. Historical data set including rainfall, pumping rates, spring discharge, and piezometric trends may be available from regional institution, and they also was used and helpful for the first stage to understanding which will be the trouble of and the time series evolution of the piezometric level in different parts of aquifer. Combining this complementary dataset through AI tools and hydrogeological modeling enables continuous monitoring and improved the recharge estimation, early draw detection, and reliable forecast for groundwater availability, supporting sustainability water resource management under changing climatic conditions. So we are planning probably also to install meteo station to evaluate also the evapotranspiration is the next the advantage steps. Demography, so how well logs support this future provision. So the calibration of demography models, well logs provide the real rheology fracture and water level data to calibrate and validate demography 3D images. Characterization of hydraulic properties, permeability, transmission, and specific yield from well tests improve model parameters. The definition of hydrostratigraphic units, logs identify aquifer layers, boundaries, and karst features for accurate conceptual modeling. Future forecasting scenarios, combined data allow reliable situation, and pumping impacts and also the climate change scenario will be improved through meteo station and other surface parameters, other network surface parameters for evaluate the evapotranspiration. The really final target is this: from prediction to water management. Early warnings for doubt, the sustainability pumping strategy, optimization of location and water, create also a system of optimization and allowing water prediction, protection of spring and protection of springs and ecosystem. You have the actual network with different points: high recharge zone, spring, monitoring well, low recharging zone in yellow, and medium recharging zone. So the prediction output example, groundwater level forecast in the next 12 months. Underline this is the observed and forecast a decrease between 100 to 18 meters by seconds in total water of aquifer. Murge aquifer at glance. Karst aquifer, so how is build up this aquifer? So what is Murge aquifer? Murge aquifer is a large karst groundwater system hosted in carbonate rocks formed mainly during the Cretaceous period. Highly permeable through the measured permeability is driven by fracture and fault, and the karstic conduits. Storage and transmitted water is really efficiently because the expansion of fracture and the connectivity of fracture is high, providing spring and base fall to river and coastal areas. So the main geological units, as we just say, from a cross-section between ovest to west, we have the Quaternary deposit, the Cretaceous limestone that contains the major aquifer. In the subsurface you have the dolomitic limestone, and in really subsurface you have impermeable formation. So the fault make the major connection between aquifer that distribution with the different piezometric level. You have different piezometric level between the central part, the first part that is connected, you see, with a small face of around 3 or 5 kilometers, and the second part that is in the Alta Murge. So we have a complex system of recharge and flow, the rainwater infiltration through fracture and sinkhole, recharging the aquifer mainly through the Murge plateau. We are studying some main emerging zones and springs, like this Sorgente del Gorgo, Sorgente di San Giorgio, and also coastal submarine discharge. We have the water balance, medium water balance input and storage capacity. We have the discharge output that actually is between these volumes, and the spring was mapping is around 300 springs. Base flow to river, the submarine discharge, and the pumping using. So, as we just said, the fault given a double rules. We have the rules to connect the different parts of aquifers, but have also the rules to be a principal form of drainage. The stratigraphic column, you have the following stratigraphic reference column for this part. You have from 0 to 1 million age to Quaternary deposit, alluvial fan deposit. So you can consider that effectively the main aquifer was in the Cretaceous unit, but the basal aquiclude is setting in Dolomite limestone of lower Cretaceous, and the aquitard was setting in calcareous sands. So with different levels, they influenced also the circulation, the fracture, and the system of fracture influenced also the circulation. You have a basin overview hydrogeological map with recharge area, main aquifer with upper Cretaceous in blue, and you have also schematic cross-section of Murge Plateau in the internal basin that, as we just say, we have this part, the upper part that is function like recharge area. In this part you have several points with confining and semi-confined aquifer, but the spilling point is resulting in the lowest part of aquifer, in the coastal discharge springs and submarine discharge. So we have also this topographic trouble that much more water was discharged in the sea. Geological topographic and condition makes this phenomenon. Much time of water, natural waters, was natural discharged in the sea. So we have some principal drainage network. We study the principal line of drainage network. We have some river, some surface river, like Bradano, Basin, and Torrente Gravino, and also Camastra. But we have also some subsurface drainage system that is invisible because was the fracture of conduit linked direct to the sea. Is when there is no barrier. Is much more important to underline that the faults have three rules in this case. So the first rule is make a barrier contact between the alto structure of part of Murge and isolated these parts. You isolated these parts because you have fine limestone that was filled, sanctioned filled the fault in this part. So is one of the explanation, because in the central part you have confined system aquifer. But when the piezometric level goes up to the fault, it seems to make the drops the barriers, and so you have a preference drainage under the sea level. So it wasn't surpassed this fault, and some parts go directly to the sea with the spilling point at the sea. So we are estimating that we have 4 or 5 liters by month. That was 400 liters by month that was lost in the sea. This is also a schematic resume of fault system and age. We have the Gravina fault, is a normal fault. It is a late Cretaceous Micene fault with extensional system, Altamure fault, and the recent fault that this is the Puglio fault, deep boundary faults, that is governing the major system of the lowest part of aquifer. Water resource assessment by this. So in this hydrogeological synthetic map, we can see we are plotting some schematic tips. We have the legend. We are plotting, for example, the recharge point expressed in millimeters by year. So all of part can be contributed by the general flow. The measure flow is in this direction. We have plotting also fault, measure recharge area, critical recharge area, municipal well fields, and you have the net infiltration map. So with this map you underline effectively how many waters by rainfall was able to infiltrated in the aquifer by year. So the measured infiltration became in this part, in the central part, also for topographic condition, but also for the permeability of the first layer surface. We have a geostatistical estimation of groundwater id, the top of groundwater. So the deepest part is in this part. We have also plotting the monitoring wells and the kriging contour. Finally, you have estimated quantity availability. We have the net recharge mean volume million cube by year. So any each 1 year the aquifer was subjected to a charge of 1,100 million meter cubes by year. The surface water contribution is this, it represented the surface of basin. Total natural availability is this. The environment outflow based by the spring and the base flow, as we just say, we are lost about 50% by the natural drainage agency. Safe exploitability is this, the estimation of population. We have an estimation of population concentration. This is for domestic use, unit consumption, annual volume. We have water resource balance, population concentration, agricultural use, and environment flow. In this case, we are showing you the hydrogeological cross-section. This cross-section was built up in this direction. We have the recharge area Murge plateau. We have the dispersion zone of fault enhancing flow between the fault 1, old normal fault, and second normal fault, between Gravina fault and another normal fault. The barrier zone. So the dispersion fault is open and calcified and acts as a conduit enhancing vertical and lateral groundwater flow. Water is dispersed and emerges as diffuse springs. Barrier zone, fault is seams by clay, calcite or less permeable rocks, act a barrier and impelling groundwater and causing water to pump up gradient and emerge at a specific point. So the measured spilling point is near to the water, so to the Adriatic Sea surface, and some part go directly to Adriatic surface. So this is one of natural travel, which will be the fourth effects on groundwater. This is a dispersion. The most effective effect is dispersion, increased permeability, diffuse spring emergence, and higher groundwater potential. You have also barrier effect, reduced permeability, ponding up gradient, and point source spring emergence. The typical emergence behavior. You have multiple small springs along the fault, and you have example in Puglio emergence. Spring allows fault zone. Springs allow fault zone in Gravina. Measure springs at base of scarps, for example, sorgenti dell'Enne or Capodacqua. Coastal submarine groundwater discharge influenced by the fault. As we just said, we have a 9 influence of coastal submarine groundwater discharge. Water resource assessment, and this is the first analysis for water resource assessment. What we are preventing to do, real-time alerts and human intervention researching from data to action, installing a series of piezometric stations with Arduino sensor network for multi-parameter station monitoring, water level, evapotranspiration evaluation, electrical conductivity, evaluation also of chemical parameters like pH and turbidity, dissolved quantity of oxygen, is one of the action possible, for example, to going on to the monitorings, critical alert, water level below critical, and you can create also a free level of alerts when you see that is a high discharge of concentration. Which will be finally one of the questions to evaluate really the volume can be stored in this aquifer. The first question is a geological question, which will be effectively the thickness of main carbonatic aquifer system in Murge Basin. So to respond to this basic question, we have tried to map, to produce aquifer thickness SOPAC map, and you see that a SOPAC map have a perfect convergence with the line of drainage, and so it's really interesting to see this map and make comparison to other hydrogeological cross-section. It's much more interesting because you can see that the measured thickness of aquifer was in the central part. Why was it in the central part? Because the normal fault created a low structural situation, so that it means that this part was faulted and was tapped down, and you have a low system, so this part have the measured thickness for aquifer. The thickness in this part is around 600 meters, especially in Colle in Santerno, in Zona Santerno, and you have the lowest part in the highest you have the lowest part where the carbonated was upped by the fault system. It's interesting to also to underline that this trapping was not works really, because the faults, the deep faults in this part allowed the natural drainage through the Adriatic Sea. So this particular hydrogeological situation. So the fourth groundwater direction is through the, you can see that the groundwater, these lines, groundwater flow direction. So you have several parts, especially in the lowest southwest, that you have groundwater flow direction in direction of Adriatic Sea. And so ISOPAC map confirms the first data, probably confirms the first data of how water was moving. The two questions is the thickness of aquifer to estimate the total volume of the total rechargeable volume. The second, how water is moving in the aquifer. So the medium the minimum thickness is around 50 meters. The maximum is around 700 meters. So the average thickness, this total basin is this. So you can multiply this value with this value. You can obtain the maximum water storage, the possibility of maximum storage aquifer. Multiply this by this and multiply for the effective bulk porosity. So as we just say, we have a different part that we can recognize. I classified aquifer carbonatids by in this central part of basin, Cretaceous and upper Cretaceous, middle layer the system with the variable thickness, high productivity in central western sector. So the geologist is the analysis, the geological and radiological and structural analysis is much more important to understand effectively which will be the maximum capacity of this aquifer to store water, and which will be the preference drainage lines, and which is the actual behavior. So we have 4 answers, which will be the actual behavior of the aquifer, and which will be the future behavior of aquifer if, for example, we are insert in a complex model evapotranspiration parameters. So the project will goes on if region will fancy that installation of evapotranspiration in all of basin, and we can send a real model and predictive model of aquifer. So one of the most important and characteristic of result is the evidence of natural drainage in the Adriatic Sea around this value by year. New caption, so to solve and to maintain this water and to not disperse this water in the Adriatic Sea, we are planning, we are suggesting to the administration to create a new planification of subsurface with new caption and internal barriers. Proposal intervention to avoid and prevent natural drainage toward the Adriatic Sea. So the scope is preserve water resource in the Murge aquifer basin by reducing and regulating the subsurface drainage towards the Adriatic Sea through integrating structure analysis, hydrogeological model, on-site testing, and natural-based intervention. So you have planning this is Murge-based boundary. You have a current situation with the actual system of drainage with karstic conduit and fracture that allow with also the structure and topographical system allows the permitted that waters flow through the sea. We can be different solution. So the first easy solution is to create a proposed intervention with drainage reduction, field barrier, and in this case field barrier 3 or 4. In this case we are planning 3, but the correct is 4 because we need another subsurface barrier here. Expected benefit: preservation of groundwater resources, reduce losses of fresh water to the sea, improve groundwater availability for communities, and this is can be a positive effects also on local economy for reduce the loss of fresh water for agriculture and ecosystem, especially for all of part near to the sea. We can increase also resilience to drought and climatic change, sustainability, and integrated water management, which will be the area that can be subjected to this intervention. So we have make a first proposal of priority ranking where this intervention can be settled. So the coastal trip near Puglio Monopoly, the main intervention is to build a subsurface barrier, block main drainage conduits. The second is Gioia Colle Pugliano, recharge. The effect of intervention is recharge enhancement. So primary goal is increasing infiltration and recharge. The second is central Murge plateau, flow dispersion structure, redirect flow inland. Cassano Santerno area, recharge basin sinkhole. We have also the trouble of sinkhole. So we have also the trouble of stability of some karstic conduit. So make this can be also ensured in another part to solve the sinkhole problems in sometimes. So the goal is enhance the infiltration capacity, coastal discharge zone. The main infiltration is the coastal protection measure, reduce submarine discharge. You can see the proposal interval linked 1 to 6 to 7. Okay, we have 7. 6 is the monitoring management, is to build a real-time wireframe monitoring with evapotranspiration, Arduino sensor, and like this. Second is proposed intervention, subsurface hydraulic barriers, construction underground barriers, upgrade recharge enhancement, flow dispersion structure, coastal discharge reduction, nature-based solution. So why we propose this intervention? So we are not foolish, but we make this consideration starting from real data. The study area is, as we just know, the study area of Murge. We have the annual summary data. Starting from 2020 to 2024, you have the population surveyed by the local aquifer, the water need demand, and the water availability supply. You have finally make the water balance. As we just say, in the last 6 years, we have the balance pass from positive data to negative data. So we are proposing, we are make this study with a precise scope to support the local administration and to support the local authority to plan the resource, to try to solve also this natural phenomenon of the water that was dispersed in the Adriatic Sea. We have also a sketch that show how the natural water, fresh water was, the demand of fresh water was used by sector. So we have a public sector, domestic, agriculture, industries, and other sectors. So you can see that the 4 different types have not much change. We have just an increase of agricultural sector and domestic sector. So we have also a time series trends. The water needs, the water balance, we are plotting the water needs, so the demands that it becomes that these 4 types of sectors. The water availability, that is the maximum water extracted by the single points, and the water balance that is in red. So you can see that the red curve, that is the result curve, is goes down in the last 5-6 years. And you have also the water stress index. The divergence of index, that means that aquifer starting was changed, was stressed, because the requirement was much more than the water availability. Where was extracted, and finally you have a cumulative water balance in the last 5 years. That is the same, is the resume graph, or this is a resume image from this graph. So we have created also the water stress aquifer index, and when this parameter is measured at 1, it means that aquifer was stressed, so the balance is negative. Management application: improve irrigation efficiency and promote water saving technologies, reduces loss in distribution network, protect the recharge areas from urbanization and contamination, continuous monitoring and periodic update. You are see also the variation in the month of 24. We can see also the water per geometric level. Water per geometric level is decrease of 9, we have a medium decrease in the aquifer, of 9 meters between these 6 years. So good, this is the basic data that driven us to make this study, this analysis, and support the region. You have also so how we connect? So we connection in two way, in three way. In the same time, we connection in three way. So the first is to planning new exploration wells. That is possible, but new exploration wells is a temporary solution, because what we want to underline that we need to the measure trouble of aquifer is the stability, the transmissivity of the aquifer and the direction of drainage, and also to block all of water that is natural drainage to sea. So probably new exploration well was only a temporary solution, or measure we can be a local solution. So the real goal is increase the security and stability of water in the aquifer, optimized also have a clear square of evapotranspiration, so is the next. Underground interconnected storage that will be stopped the natural flow to the Adriatic Sea, monitoring and integration. And so finally have a clear governance of the water fresh resource. So we have a probably in implementation roadmap, construct interconnected storage system and recharge structure, monitoring evapotranspiration, and built network for monitoring evapotranspiration and piezometric level, continuous optimization for stability and resilience. So this is something that we are presenting in this. We are hoping to go on to the collaboration to Puglia region and the local authority. Thanks for attention.